School of Management Studies IGNOU presents an audiobook on the course MMPC 010 titled Managerial Economics for MBA Program. Presenting Block 3 titled Production and Cost Analysis. Unit 7 Production Function.
Objectives. After going through this unit, you should be able to familiarize with the concepts and rules relevant for production decision analysis, understand the economics of production, understand the set of conditions required for efficient production. Introduction. Production process involves the transformation of inputs into output. The inputs could be land, labor, capital, entrepreneurship, etc. And the output could be goods or services. In a production process, managers take 4 types of decision. A. Whether to produce or not. B. How much output to produce. C. What input combination to use. And D. What type of technology to use. This unit deals with the analysis of managers' decision rules concerning C and D. In this unit, we shall begin with a general discussion of the concept of production function. The analysis of this unit mainly focuses on the firms that produce a single product. Analysis on decisions related to multi-product firms is also given briefly. The nature of production when there is only one variable input is taken up first. We then move on to the problem of finding optimum combination of inputs for producing a particular level of output when there are 2 or more variable inputs. You will also learn about the production decisions in case of product mix of multi-product firms. The unit concludes with various functional forms of production frequently used by economists and their empirical estimation. Production function. Suppose we want to produce apples. We need land, seedlings, fertilizer, water, labor, and some machinery. These are called inputs or factors of production. The output is apples. In general, a given output can be produced with different combinations of input. A production function is the functional relationship between inputs and output. It shows the maximum output which can be obtained for a given combination of inputs. It expresses the technological relationship between inputs and output of a product. In general, we can represent the production function for a firm as Q is equals to F bracket open x1 x2 till xn bracket closed, where Q is the maximum quantity of output, x1 x2 till xn are the quantities of various inputs, and F stands for functional relationship between inputs and output. For the sake of clarity, let us restrict our attention to only one product produced using either one input or 2 inputs. If there are only 2 inputs, capital K and labor L, we write the production function as Q is equals to F into L, K. This function defines the maximum rate of output Q obtainable for a given rate of capital and labor input. It may be noted here that outputs may be tangible like computers, television sets, etc. or it may be intangible like education, medical care, etc. Similarly, the inputs may be other than capital and labor. Also, the principles discussed in this unit apply to situations with more than 2 inputs as well. Economic efficiency and technical efficiency. We say that a firm is technically efficient when it obtains maximum level of output from any given combination of inputs. The production function incorporates the technically efficient method of production. A producer cannot decrease one input and at the same time maintain the output at the same level without increasing one or more inputs. When economists use production functions, they assume that the maximum output is obtained from any given combination of inputs. That is, they assume that production is technically efficient. On the other hand, we say a firm is economically efficient when it produces a given amount of output at the lowest possible cost for a combination of inputs, provided that the prices of inputs are given. Therefore, when only input combinations are given, we deal with the problem of technical efficiency, that is, how to produce maximum output. On the other hand, when input prices are also given in addition to the combination of inputs, we deal with the problem of economic efficiency, that is, how to produce a given amount of output at the lowest possible cost. One has to be careful while interpreting whether a production process is efficient or inefficient. Certainly, a production process can be called efficient if another process produces the same level of output using one or more inputs, other things remaining constant. However, if a production process uses less of some inputs and more of others, the economically efficient method of producing a given level of output depends on the prices of inputs. Even when two production processes are technically efficient, one process may be economically efficient under one set of input prices, while the other production process may be economically efficient at other input prices. Let us take an example to differentiate between technical efficiency and economic efficiency. An ABC company is producing ready-made garments using cotton fabric in a certain production process. It is found that 10% of fabric is wasted in that process. An engineer suggested that the wastage of fabric can be eliminated by modifying the present production process. To this suggestion, an economist reacted differently, saying that if the cost of wasted fabric is less than that of modifying production process, then it may not be economically efficient to modify the production process. Short run and long run. All inputs can be divided into two categories. 1. Fixed inputs and 2. Variable inputs. A fixed input is one whose quantity cannot be varied during the time under consideration. The time period will vary depending on the circumstances. Although any input may be varied no matter how short the time interval, the cost involved in augmenting the amount of certain inputs is enormous, so as to make quick variation impractical. Such inputs are classified as fixed and include plant and equipment of the firm. On the other hand, a variable input is one whose amount can be changed during the relevant period. For example, in the construction business, the number of workers can be increased or decreased on short notice. Many builder firms employ workers on a daily wage basis, and frequent change in the number of workers is made depending upon the need. The amount of milk that goes in the production of butter can be altered quickly and easily and is thus classified as a variable input in the production process. Whether or not an input is fixed or variable depends upon the time period involved. The longer the length of the time period under consideration, the more likely it is that the input will be variable and not fixed. Economists find it convenient to distinguish between the short run and the long run. The short run is defined to be that period of time when some of the firm's inputs are fixed, since it is most difficult to change plant and equipment among all inputs. The short run is generally accepted as the time interval over which the firm's plant and equipment remain fixed. In contrast, the long run is that period over which all the firm's inputs are variable. In other words, the firm has the flexibility to adjust or change its environment. Production function with one variable input. Consider the simplest two-input production process, where one input with a fixed quantity and the other input with its variable quantity. Suppose that the fixed input is the service of machine tools, the variable input is labor, and the output is a metal part. The production function in this case can be represented as Q is equals to F into KL, where Q is output of metal parts, K is service of the 5 machine tools, and L is labor, where K is fixed input and L is variable input. The variable input can be combined with the fixed input to produce different levels of output: total, average, and marginal products. The production function shows us the maximum total product, TP, that can be obtained using different combinations of quantities of inputs. Suppose the metal parts company decides to know the output level for different input levels of labor using fixed 5 machine tools. Two other important concepts are the average product AP and the marginal product MP of an input. The AP of an input is the TP divided by the amount of input used to produce this amount of output. Thus, AP is the output-input ratio for each level of variable input usage. The MP of an input is the addition to TP resulting from the addition of 1 unit of input when the amounts of other inputs are constant. Relationship between TP, MP and AP curves. We can establish the following relationship between TP, MP and AP curves. 1a. If MP is greater than 0, TP will be rising as L increases. The TP curve begins at the origin, increases at an increasing rate over the range 0 to 3 and then increases at a decreasing rate. The MP reaches a maximum at 3, which corresponds to an inflection point X on the TP curve. At the inflection point, the TP curve changes from increasing at an increasing rate to increasing at decreasing rate. B. If MP is equals to 0, TP will be constant as L increases. The TP is constant between workers 6 and 7. C. If MP is less than 0, TP will be declining as L increases. The TP declines beyond 7. Also, the TP curve reaches a maximum when MP is equals to 0 and then starts declining when MP is less than 0. 2. MP intersects AP. MP is equals to AP at the maximum point on the AP curve. This occurs at labor input rate 4.5. Also, observe that whenever MP is greater than AP, the AP is rising up to number of workers 4.5. It makes no difference whether MP is rising or falling. When MP is less than AP, the AP is falling. Therefore, the intersection must occur at the maximum point of AP. It is important to understand why. The key is that AP increases as long as the MP is greater than AP and AP decreases as long as MP is less than AP. Since AP is positively or negatively sloped depending on whether MP is above or below AP, it follows that MP is equals to AP at the highest point on the AP curve. This relationship between MP and AP is not unique to economics. Consider a cricket batsman, say Anil Kumar, who is averaging 50 runs in 10 innings. In his next innings, he scores 100. His marginal score is 100 and his average will now be above 50. More precisely, it is 54. That is 50 into 10 plus 100 divided by 10 plus 1, which is equals to 600 by 11. This means when the marginal score is above the average must increase. In case he had scored 0, his marginal score would be below the average and his average would fall to 45.5, that is 500 by 11, which is 45.45. Only if he had scored 50 would the average remain constant and the marginal score would be equal to the average. The law of diminishing marginal returns. As the number of units of the variable input increases, the other inputs held constant, fixed, there is a point beyond which the MP of the variable input declines. Observe that MP was increasing up to the addition of 4th worker. Beyond this, the MP decreases. What this law says is that MP may rise or stay constant for some time, but as we keep increasing the units of variable input, MP should start falling. It may keep falling and turn negative or may stay positive all the time. Consider another example for clarity. Single application of fertilizers may increase the output by 50%, a second application by another 30%, and the third by 20%, and so on. However, if you were to apply fertilizer 5 to 6 times in a year, the output may drop to 0. 3 things should be noted concerning the law of diminishing marginal returns. 1. This law is an empirical generalization, not a deduction from physical or biological laws. 2. It is assumed that technology remains fixed. The law of diminishing marginal returns cannot predict the effect of an additional unit of input when technology is allowed to change. 3. It is assumed that there is at least one input whose quantity is being held constant. In other words, the law of diminishing marginal returns does not apply to cases where all inputs are variable. Stages of production. Based on the behavior of MP and AP, economists have classified production into three stages. Stage 1, MP is greater than 0, AP rising, thus MP is greater than AP. Stage 2, MP is greater than 0, but AP is falling. MP is less than AP, but TP is increasing. Stage 3, MP is less than 0, in this case, TP is falling. Production function with two variable inputs. Now we turn to the case of production where two inputs, say capital and labor, are variable. Although we restrict our analysis to two variable inputs, all of the results hold for more than two also. We are restricting our analysis to two variable inputs because it simply allows us the scope for graphical analysis. When analyzing production with more than one variable input, we cannot simply use sets of AP and MP curves like those discussed in previous section, because these curves were derived holding the use of all the other inputs fixed and letting the use of only one input vary. If we change the level of fixed input, the TP, AP, and MP curves would shift. In the case of two variable inputs, changing the use of one input would cause a shift in the MP and AP curves of the other input. For example, an increase in capital would probably result in an increase in the MP of labor over a wide range of labor use. Production isoquants. In the Greek, the word iso means equal or same. A production isoquant, equal output curve, is the locus of all those combination of two inputs which yields a given level of input. With two variable inputs, capital and labor, the isoquant gives the different combinations of capital and labor that produces the same level of output. Marginal rate of technical substitution. As we have seen, generally there are a number of ways that a particular output can be produced. The rate at which one input can be substituted for another input, if output remains constant, is called the marginal rate of technical substitution, MRTS. It is defined in case of two inputs, capital and labor, as the amount of capital that can be replaced by an extra unit of labor without affecting total output. MRTSL for K is equals to upper delta K by upper delta L. It is customary to define the MRTS as a positive number since upper delta K divided by upper delta L, the slope of the isoquant is negative. Over the relevant range of production, the MRTS diminishes. That is, more and more labor is substituted for capital while holding output constant. The absolute value of upper delta K by upper delta L decreases. For example, let us assume that 10 pairs of shoes can be produced using either 8 units of capital and 2 units of labor, or 4 units each of capital and of labor, or 2 units of capital and 8 units of labor. The MRTS has decreased because capital and labor are not perfect substitutes for each other. Therefore, as more of labor is added, less of capital can be used, while keeping the output level constant. There is a simple relationship between MRTS of labor for capital and the marginal product MPK and MPL of capital and labor respectively, since along an isoquant, the level of output remains the same if upper delta L units of labor are substituted for upper delta K units of capital. The increase in output due to upper delta L units of labor should match the decrease in output due to a decrease of upper delta K units of capital. In other words, along an isoquant, upper delta L into MPL is equals to upper delta K into MPK, which is equal to upper delta K by upper delta L is equals to MPL by MPK. However, as we have seen earlier, upper delta K by upper delta L is equal to MRTSL for K, and hence we get the following expression for MRTS of L for K as the ratio of the corresponding marginal products. MRTSL for K is equals to MPL by MPK. There are vast differences among inputs in how readily they can be substituted for one another. For example, in some extreme production process, one input can perfectly be substituted for another, whereas in some other extreme production process, no substitution is possible. On the other hand, in most of the production process, what we see is imperfect substitution of inputs. The optimal combination of inputs. As said earlier, in the introduction of this unit, one of the decision problems that concerns a production process manager is which input combination to use. That is, what is the optimal input combination? While all the input combinations are technically efficient, the final decision to employ a particular input combination is purely an economic decision and rests on cost. Thus, the production manager can make either of the following two input choices of decisions. 1. Choose the input combination that yields the maximum level of output with a given level of expenditure. 2. Choose the input combination that leads to the lowest cost of producing a given level of output. Thus, the decision is to minimize cost. Cost subject to an output constraint or maximize the output subject to a cost constraint. We will now discuss these two fundamental principles. Before doing this, we will introduce the concept of ISO cost, which shows all combinations of input that can be used for a given cost. ISO cost lines. Recall that a universally accepted objective of any firm is to maximize profit. If the firm maximizes profit, it will necessarily minimize cost for producing a given level of output or maximize output for a given level of cost. Suppose there are two inputs, capital K and labor L, that are variable in the relevant time period. What combination of KL should the firm choose in order to maximize output for a given level of cost? If there are two inputs, KL, then given the price of capital PK and the price of labor PL, it is possible to determine the alternative combinations of KL that can be purchased for a given level of expenditure. Suppose C is total expenditure, then C is equals to PL into L plus PK into K. The straight line is called the ISO cost line or equal cost line. It shows the alternative combinations of KL that can be purchased for the given expenditure. Optimal combination of inputs, the long run. When both capital and labor are variable, determining the optimal input rates of capital and labor requires the technical information from the production function, that is, the ISO quants be combined with market data on input prices, that is, the ISO cost function. If we superimpose the relevant ISO cost curve on the firm's ISO quant map, we can readily determine graphically as to which combination of inputs maximize the output for a given level of expenditure. Regardless of the production objective, efficient production requires that the ISO quant be tangent to the ISO cost function. If the problem is to maximize output subject to a cost constraint or to minimize cost for a given level of output, the same efficiency condition holds true in both situations. Intuitively, if it is possible to substitute one input for another to keep output constant while reducing total cost, the firm is not using the least cost combination of inputs. In such a situation, the firm should substitute one input for another. The ISO cost ISO quant framework described lends itself to various applications. It demonstrates simply and elegantly when relative prices of inputs change, managers will respond by substituting the input that has become relatively less expensive for the input that has become relatively more expensive. On average, we know that compared to developed countries like the US, UK, Japan, and Germany, labor in India is less expensive. It is not surprising, therefore, to find production techniques that on average use more labor per unit of capital in India than in the developed world. For example, in construction activity, you see around in your city, inexpensive workers do the job that in developed countries is performed by machines. Returns to scale. Another important attribute of production function is how output responds in the long run to changes in the scale of the firm, that is, when all inputs are increased in the same proportion. How does output change? Clearly, there are three possibilities. If output increases by more than an increase in inputs, that is by more than 10%, then the situation is one of increasing returns to scale, IRS. If output increases by less than the increase in inputs, then it is a case of decreasing returns to scale, DRS. Lastly, output may increase by exactly the same proportion as inputs. For example, a doubling of inputs may lead to a doubling of output. This is a case of constant returns to scale, CRS. There is no universal answer to which industries will show what kind of returns to scale. Some industries like public utilities, telecom and electricity generation show increasing returns over large range of output, whereas other industries exhibit constant or even decreasing returns to scale over the relevant output range. Therefore, whether an industry has constant, increasing or decreasing returns to scale is largely an empirical issue. Functional forms of production function. One of the first tasks is to select a functional form, that is, the specific relationship among the relevant economic variables. We know that the general form of production function is Q is equals to F into KL, where Q is equals to output, K is capital and L is labor. Although a variety of functional forms have been used to describe production relationships, only the Cobb-Douglas production function is discussed here. The general form of the Cobb-Douglas function is expressed as Q is equals to AK to the power alpha, L to the power beta, where A, alpha and beta are the constants that, when estimated, describe the quantitative relationship between the inputs K and L and output Q. Types of statistical analysis. Once a functional form of a production function is chosen, the next step is to select the type of statistical analysis to be used in its estimation. Generally, there are three types of statistical analysis used for estimation of a production function. These are A. Time series analysis. The amount of various inputs used in various periods in the past and the amount of output produced in each period is called time series data. For example, we may obtain data concerning the amount of labor, the amount of capital, and the amount of various raw materials used in the steel industry during each year from 1970 to 2000. On the basis of such data and information concerning the annual output of steel during 1970 to 2000, we estimate the relationship between the amounts of the inputs and the resulting output using regression techniques. Analysis of time series data is appropriate for a single firm that has not undergone significant changes in technology during the time span analyzed. That is, we cannot use time series data for estimating the production function of a firm that has gone through significant technological changes. There are even more problems associated with the estimation a production function for an industry using time series data. For example, even if all firms have operated over the same time span, changes in capacity, inputs, and outputs may have proceeded at a different pace for each firm. Thus, cross-section data may be more appropriate. B. Cross-section analysis. The amount of inputs used and output produced in various firms or sectors of the industry at a given time is called cross-section data. For example, we may obtain data concerning the amount of labor, the amount of capital, and the amount of various raw materials used in various firms in the steel industry in the year 2020. On the basis of such data and information concerning the year 2020, output of each firm, we may use regression techniques to estimate the relationship between the amounts of the inputs and the resulting output. C. Engineering analysis. In this analysis, we use technical information supplied by the engineer or the agricultural scientist. This analysis is undertaken when the above two types do not suffice. The data in this analysis is collected by experiment or from experience with day-to-day working of the technical process. There are advantages to be gained from approaching the measurement of the production function from this angle, because the range of applicability of the data is known, and unlike time series and cross-section studies, we are not restricted to the narrow range of actual observations. Limitations of different types of statistical analysis. Each of the methods discussed above has certain limitations. 1. Both time series and cross-section analysis are restricted to a relatively narrow range of observed values. Extrapolation of the production function outside that range may be seriously misleading. 2. Another limitation of time series analysis is the assumption that all observed values of the variables pertains to one and the same production function. In other words, a constant technology is assumed. In reality, most firms or industries, however, find better, faster, or cheaper ways of producing their output. As their technology changes, they are actually creating new production functions. One way of coping with such technological changes is to make it one of the independent variables. 3. Theoretically, the production function includes only efficient combination of inputs. If measurements were to conform to this concept, any year in which the production was less than nominal would have to be excluded from the data. It is very difficult to find a time series data which satisfy technical efficiency criteria as a normal case. 4. Engineering data may overcome the limitations of time series data, but mostly they concentrate on manufacturing activities. Engineering data do not tell us anything about the firm's marketing or financial activities, even though these activities may directly affect production. 5. In addition, there are both conceptual and statistical problems in measuring data on inputs and outputs. It may be possible to measure output directly in physical units such as tons of coal, steel, etc. In case more than one product is being produced, one may compute the weighted average of output, the weights being given by the cost of manufacturing these products. In a highly diversified manufacturing unit, there may be no alternative but to use the series of output values corrected for changes in the price of products. One has also to choose between gross value and net value. It seems better to use net value added concept instead of output concept in estimating production function, particularly where raw material intensity is high. The data on labor is mostly available in the form of number of workers employed or hours of labor employed. The number of workers data should not be used because it may not reflect underemployment of labor and they may be occupied but not productively employed. Even if we use man-hours data, it should be adjusted for efficiency factor. It is also not advisable that labor should be measured in monetary terms as given by the expenditure on wages, bonus, etc. The data on capital input has always posed serious problems. Net investment, that is, a change in the value of capital stock, is considered most appropriate. Nevertheless, there are problems of measuring depreciation in fixed capital, changes in quality of fixed capital, changes in inventory valuation, changes in composition and productivity of working capital, etc. Finally, when one attempts an econometric estimate of a production function, one has to overcome the standard problem of multi-collinearity among inputs, autocorrelation, homoscedasticity, etc. Managerial uses of production function. There are several managerial uses of the production function. It can be used to compute the least cost combination of inputs for a given output or to choose the input combination that yields the maximum level of output with a given level of cost. There are several feasible combinations of input factors and it is highly useful for decision makers to find out the most appropriate among them. The production function is useful in deciding on the additional value of employing a variable input in the production process. So long as the marginal revenue productivity of a variable factor exceeds its price, it may be worthwhile to increase its use. The additional use of an input factor should be stopped when its marginal revenue productivity just equals its price. Production functions also aid long-run decision-making. If returns to scale are increasing, it will be worthwhile to increase production through a proportionate increase in all factors of production, provided there is enough demand for the product. On the other hand, if returns to scale are decreasing, it may not be worthwhile to increase the production through a proportionate increase in all factors of production, even if there is enough demand for the product. However, it may in the discretion of the producer to increase or decrease production in the presence of constant returns to scale, if there is enough demand for the product. Summary. A production function specifies the maximum output that can be produced with a given set of inputs. In order to achieve maximum profits, the production manager has to use optimum input-output combination for a given cost. In this unit, we have shown how a production manager minimizes the cost for a given output in order to maximize the profit. Also, we have shown how to maximize the output at a given level of cost. The law of diminishing marginal returns states that as equal increments of variable input are added to fixed input, a point will eventually be reached where corresponding increments to output begin to decline. We have also seen the relations between the marginal product, average product, and total product. There are 3 stages of production. Stage 1 is characterized by MP is greater than 0 and MP greater than AP. Stage 2 is characterized by MP greater than 0 and MP less than AP. Stage 3 is characterized by MP less than 0. The economically meaningful range is Stage 2. The production manager maximizes the profit at a point where the value of marginal product equals the price of the output. A production isoquant consists of all the combination of 2 inputs that will yield the same maximum output. The marginal rate of technical substitution is upper delta K by upper delta L, holding output constant. The law of diminishing marginal rate of substitution implies the rate at which one input can be substituted for another input if output remains constant. An isocost line consists of all the combinations of input which have the same total cost. The absolute slope of the isocost line is the input price ratio. Returns to scale, a long-run concept, involves the effect on output of changing all inputs by same proportion and in the same direction.
We were listening to the audiobook by the School of Management Studies IGNOU for MBA program. Course code MMPC 010, titled Managerial Economics. Course Coordinator Dr. Leena Singh. Voiceover by Renuka. Edited by Savita. Program assisted by Tarannum Jahan. Program produced by Dr. Manoj Kumar Singh. This program was brought to you by Electronic Media Production Center of Indira Gandhi National Open University.